see this. Check. Okay, you at home, can y'all hear me, see me, and see my screen?
Yes, sir.
Okay, good. Thank you. All right, it's 101. So let's get started here. Boy, we got three in class here. We only have 2 online. That's weird. Normally we have a lot more. So, okay, let's talk about, this is our last week of lecture. And then next week is our final. So our final will take place on Wednesday. We talked about this already, 12:30 to 3:15. We do not have class on Monday. All right, so we'll have today, then we'll have this Wednesday, and that will be it. All right, in terms of us meeting for material. So my intention is today we're going to do more sequences, series, and then on Wednesday, maybe a little bit more. And then I want to talk about the final, pretty much spend all Wednesday, well, most of Wednesday talking about the final. So plan on me presenting you with a review, something to go over on Wednesday. All right. All right, let's get down to business here. So we were talking about sequences and series, or sequences last time, and we're going to continue with sequences, and then we'll get into series. So the thing we were doing was kind of fun. It was, I would give you a sequence of numbers, and then you would try and come up with a formula for it, right? So let's just kind of remind ourselves by doing an example. So I want us to find the formula A sub n for this sequence. Shall we start out nice? Let's do -2/3. Let's do 4/9, -6/27, +8/81, ... So can we come up with a formula that would generate this sequence of numbers? So what do you see? What do you tell me what you're seeing, kind of how you know, how are you approaching this? Okay, so you're looking at all the denominators and they look like they're all powers of 3, exponential, right? These are all powers of 3, right? Okay, good. What else do you recognize or see? The signs are alternating, and we know how to do that, right? We know how to make that happen. We're going to do like a -1 raised to something. Okay, so we've got the alternating. I'll just put it here. It alternates. It alternates, and it starts what with positive? It starts negative. Starts negative. Okay, we'll have to address that. Okay, what else do you see? The numerator, is it exponential?
Yeah, like the example we gave about 1, 1.
So look, I agree that the denominators are all powers of 3. 3 to the first power, 3 squared, 3 cubed, 3 to the fourth. But is that what's happening in the numerator? It's going up by a common amount each time, though. And that was a different type of thing, right? That was anytime you have a common jump that we see. Hi, Carissa. Oh, hey, no, it's good. We were just talking about, we're actually gonna have more people here face to face than online today. Let's see, we're jumping by 2 each time, right? So when I say 2, I'm ignoring the negative, okay? The negative positive, because that part of it is the alternating part. I'm really just looking at the numbers, 2, 4, 6, 8, okay? That keeps jumping by 2. And so we know how to make things jump by a certain amount. We have to do, you know, like if the jump is 2, we're going to need a 2n. If the jump was 3, we need a 3n. If the jump is 5, we need a 5n. Okay. So let's put all this together. Let's come up with our formula. First, let's, Greg, Hugo, Josiah, Carissa, right? I want to make sure I got that. So I knew 4 names at the end of the semester. All right. So we want to, let's get the alternating part first. So to make it start negative, we will use -1 to what power? Remember, n is going to start with a 1, right? To the n, exactly. So if we plug an n in here, then of course, when we plug in 1, we'll get -1 to the first power, which is negative. When we plug in 2, we'll get -1 squared, which will be positive. Plug in 3, we get -1 cubed, which will be negative. So that should take care of the alternating starting negative. And then let's take care of the numerator going up by 2. So I know I need a 2n, and it needs to start with 2, right? So is this going to work, or do I need to add or subtract something? This should work, because if I plug in 1 for n here, I get 2n, which are 2 times 1, which is 2. When I plug in 2, I get 4. When I plug in 3, I get 6. So I'm just going to put 2n. I don't really need the parentheses, but I'll put it there like that. That should take care of the alternating. That should take care of the numerator. And now I just need the denominator. And that should be 3 to the n, because they're all powers of 3, starting with what, 1, then 2, then 3, then 4. So I just need it to count up. Okay. And that's it. That's our formula right there. Are there any questions?
When we're going up or down a certain amount, it's going to change what's in front of the end.
Yes. Yep. So like if this was, let's say 3, 6, 9, 12, jumping by 3, it would be 3n. Now you might have to add or subtract from that. Yeah, let me do a different one, and then we'll. Any other questions on this? No? Okay, let's do another one. So let's find a sub n for this. Okay, so let me do it this way. We'll go 7 over 10 negative 11 over 100. Then let's do 15 over 1,000. And then negative 19 over 10,000. ... This is just a slightly different variation, just so we can address your question here. So patterns, when I'm doing these, I always look for the alternating first. Does it alternate? If it does, let's go ahead and establish that first. So it alternates. It starts with a positive this time, right? So that means I'm going to need a -1 to what power? You can do n minus 1, or you can do n plus 1. You can also do n minus 3 or n plus 3. It's n plus or minus any odd number. So let me try n. I'll do -1 since you said -1. N minus 1. Think about what happens. If you plug in 1, 1 minus 1 is 0. And -1 to the 0 is 1. Right? Because anything to the 0 is 1. If I plug in 2, I get 2 take away 1, that's 1. -1 to the first power, that's negative. So that should give me this. When I plug in 3, I should get a positive. Does that make sense, everyone? Yes? Do y'all see how I'm putting a +1 wouldn't change anything either, though? If I did +1 here, think about it. If that's a +1, if I plug in 1, 1 plus 1 is 2. And so now you're going to still have a positive first. Okay, now look at the numerators. Forget the signs, just look at the numerators, 7, 11, 15, 19. Those are all jumping by 4, aren't they? So since these all jump by 4, right, we're adding 4. That means I'm going to need a 4n. But if I plug in 1 right now, I'm going to get 4, and I need to start at 7. So how do I change this from a 4 to a 7? Just add 3. Good. And you can check it, right? Just plug in 1, you should get 7. Yeah, we got 7. Plug in 2, you should get 8, 9, 10, 11. You get 11. And then the denominators. Yeah, those are all just powers of 10, right? 10 to the first, 10 squared, 10 cubed. So this will just be 10 to the n. All right. Makes sense? All right, all right. So we talked last time, let me bring up the notes. We talked last time, just brush through this quickly. Where was it? Right, the whole idea that a sequence is really a function that goes from the natural numbers into the real numbers. You take a natural number, it spits out a number. I showed you examples of the notation that we use and how you can generate the list. And then I gave you a bunch of examples and we tried to come up with formulas for each of them. That's kind of where we are right now, right? Okay, everything we've done up this far, these are called explicit formulas for sequences, because I'm giving you a sequence, we come up with the actual formula for it. Or if I gave you the formula, it would be easy to generate the sequence by just plugging in 1, 2, 3, 4, right? You could just generate it, no problem. That's not the only type of sequence there is. There is something called a recursive sequence. Recursive sequences. And the way that recursive sequences work is that instead of me giving you a formula that gives you each one of them, what we do instead is I tell you what the first one is, maybe I tell you what the first 2 numbers are, whatever, and then I tell you what all of them look like from there on out. So let me give you an example. Let's say I let a sub 1, so the first number of my sequence, let's just say that that's the number 1. Let's call the second number, I'm just making this up, 1 also. And then here's what I'm going to tell you. A sub n will be equal to a sub n minus 1 plus a sub n minus 2 for n greater than or equal to 3. That is an example of what we call a recursive sequence. Now, I know this looks weird when you first see it, but let me explain what's happening here. I'm telling you what the first term in the sequence is. So I'm telling you the first number is a 1, okay? And then the second number is also 1. Now, to get the third number, I don't tell you what it is, right? But I give you a formula. And look at what this formula says. It says a sub n is equal to a sub n minus 1 plus a sub n minus 2. And this is the formula we use whenever n is greater than or equal to 3. Okay, all right, so what in the world? What does that mean? Well, let's use that formula. Let's try down here to figure out what a sub 3 is. Well, a sub 3, according to this formula, should be what? A sub 3 minus 1, which will be 2, plus a sub 3 minus 2, right? I'm just following this formula, replacing n with 3. This is a sub 3 minus 1 is 2, plus a sub 1, right? But doesn't this just mean that to find the third one, you're just going to add the second one and the first one together, right? And we already know the first and second one, don't we? So what should the third one be? 2, right? Now, what about the fourth one? We could do the same game, right? The fourth one should be the what? 4 minus 1. So the third one plus the second one, right? So in order to find this fourth one, I just have to add up the second and the third one together, which would be 3. And now we don't really need to write them down. What would the next one be? 5, right? You're adding 3 and 2 to get 5, and then add those two up, you get the next one, 8. Those two, you get 11, no, 13. 21, and you could keep going, right? Y'all recognize this? Y'all ever seen this before? This is a very special sequence. Anyone ever seen that sequence before? No? Okay. So this is famous in mathematical sequences. It's a very well-known one. Even people who aren't really mathy people may have heard of this. It's called the Fibonacci sequence. Y'all ever heard that ring a bell? Fibonacci? I think I'm spelling this wrong. I think it's N-A-C-C-I. I think that's right. Fibonacci. This is a famous sequence, but really, I mean, it's in the big picture of sequences, it's just a sequence, all right? There's nothing really special here. Like I could have, if we wanted to make a different recursive sequence, not the Fibonacci, let's do a different one, then we'll talk more about Fibonacci. Let me just make up a new recursive sequence, okay? This one, okay, this example, I'm going to let the first number be 4. I'm going to let the second number be 1. And I'm going to even give you the third number, okay? And I'm going to tell you that that is 0. And then I'm going to give you a formula. If you want the nth one, you're going to do twice the n minus 1 plus the a sub n minus 2. And then I would like for you to subtract the a sub n minus 3. And this formula is good when n is greater than or equal to 4. Do you get the idea of how recursive works? I have to give you some information about the first few terms, and then I tell you how you can build out the rest of the terms from those. So let's write this out. The first term here is a 4, then a 1, then a 0, right? So this says to get the next one, I'll do one of these by hand. To get the fourth one, I need twice the what? A sub 3 plus a sub 2, right? And then minus a sub 1. All right. So for this particular problem, this would be twice, what's a sub 3? 0 plus a sub 2, which is 1, and then minus 4. So what would that be? Negative 3. That would be your next piece, okay? And now you could get the next one, which would be let's see if we can do this in our head. The fifth one, right? The fifth one would be twice the fourth one plus the third one minus the second one, right? So what's twice the, twice this one would be -6 plus the one before that one, which would be 0, and then take away the one before that, which would be -7, right? -6, take away one more, -7. And then we can continue to build this, all right? That is just another example of a recursive sequence. This has no name to it because I just made it up, all right? It's not a famous one. It's just one, okay? It's just a recursive sequence. All right, so Fibonacci, I don't want to get too much into Fibonacci. I'll just tell you that one of the things that is kind of special about it, that sequence of numbers, 1, 1, 2, 3, 5, 8, 13, 21. One of the famous things about this is that if you were to start to draw, watch what I'm going to do here. I'm going to draw something for you. I'm going to draw a square, and I'm going to put the number 1 inside of it. And when I put the number 1 inside of it, I'm telling you that the length of the sides of that square, each length is 1. Okay. So now if I draw this square, if I tell you this right here is a square, also, what can you tell me about the number that should be inside of it? It's a square, so that has to be 1 also, right? Okay, now if I put this here and I tell you that that is also a square, what number goes inside? 2. Well, 4 is the area, but I'm saying the number inside represents the lengths of the sides. So that should be a 2, right? Each side has a length of 2. Now, if I draw this and I tell you that that's a square, what would that be? 3, right? Because you're doing the little 2 here, right? And then you add this one, and that would be 3. And I'm going to start going around. So this next one, if I tell you that this is a square, you're going to put the number 5 in here. Oops, 5, right? The 3 and then the 1 and the 1. So 5. If I keep going around here, if I tell you that this is a square, 8, 13, 21, and I could keep going, right? And you see the Fibonacci sequence in there? 1, 1, 2, 3, 5, 8, 13. So the way you work now is you start with that first square and you put a dot in that corner, top right corner of that first square we drew. And then what I'm going to do is I'm going to connect across the square. I'm going to connect it with an arc curve. And then I'm going to connect across that one with a curve. And then across this one with a curve. And this one, and this one, and this one, and this one, this one. And you get what's called the golden spiral. And there's something about that spiral that's very special, and that is it has been studied, and some people have been able to show that in nature, things grow this way. So like if you were to look at we'll probably be able to look up something real quick here on the web. Let's put in golden spiral seashell. Oops. So like the way that a shell grows, right? When you look at a shell, a cross section of a shell, it does not grow in a perfect spiral, meaning it doesn't do this. It doesn't spiral out. Notice the space between these spirals is pretty much staying the same the whole time, right? This space, distance from here to here, distance from here to here. That seems like that distance is constant here, right? That's not the way it works in nature. In nature, you have a very tight spiral, and then it starts to spread out and open up, right? And it seems like it follows the pattern of the Fibonacci sequence. the ratio at which it spreads out is consistent with this sequence. We're not quite sure why, but that's what makes it a special sequence. Now, I will tell you, when I was a student, I was presented with this and it was like, oh, the golden ratio or the golden spiral and the Fibonacci sequence, and it appears in nature all over the place. I've actually seen a lot of stuff lately in the last 5 years, 10 years, where there's been an argument that, you know what, no, I think we're searching too hard. Like, it has nothing to do with the Fibonacci sequence. So it's kind of a debatable thing, but it at least is interesting. It gets people to at least pay attention to a sequence. This also has something to do with what's called the golden ratio. Have you all ever heard of that before? The golden ratio. So I'm going to put that here, golden ratio. So the golden ratio, I don't want an image. I want, they don't have the, yeah, it's a number. You know how you've learned like pi, right? And E are these special numbers. There's another number called phi or phi. It depends on, people pronounce it different ways. Phi or phi, and it's the golden ratio. And I'm trying to see where, yeah, here it is. So this special number in math. So think of this as like, you know, pi is approximately 3.1415. And we all accept that and we're okay with that. This number phi or phi.
Is this the one, the 1.6?
Yep. Yep, 1.618 approximately. That is what's called the golden ratio. And the way you can think about the golden ratio is this. A ratio is like a fraction, right? Pretty much. So if you were to think of, if I had a rectangle and I told you that this length right here from here to here was 1, and then I told you that this length from here to here was 1.618, then the ratio of these two sides would be, of this side to this side would be 1.618. If I took this side and divided by that, right? That would be the ratio. So that rectangle that I just drew follows the golden ratio. And it's thought that the golden ratio is like the most appealing ratio visually. Again, it's one of those things where it's like, okay, you know, like the Greeks, I believe, used this a lot in the way they built things. They said, well, what ratio do we use for our rectangles? This is the one. So where does this 1.618 comes from? Where does it come from? What it comes from is this. You take this number and divide it by the one in front of it. So if you have your calculator, well, let's start a little sooner. Let's start a little sooner. Let's go with, let's start with here. If we take 2 and divide it by 1, right? 2 divided by 1, that'd be 2. Now do 3 divided by 2, and you get 1.5. Then do 5 divided by 3. Y'all following what I'm doing here? Oh, is my calculator dead? I think my calculator's dead. Well. All right, so 5 divided by 3, 1.6666, right? Do 8 divided by 5, 1.6. Now do 13 divided by 8, 1.625. Okay, now 21 divided by 13. 1.615-ish. Okay, so if we kept doing this, do you see these numbers on top? They're headed somewhere, right? It looks like it's getting closer and closer to something. Well, it's actually, that's the way we define phi. The golden ratio is whatever those ratios are headed towards. That's the golden ratio. So interesting, weird, but it's just an example of a sequence. All right. Next thing I want to talk about. So we've got We got the idea of a recursive sequence, right? And you can make up your own. I mean, it doesn't matter. You can say, hey, here's the first two, here's the first three, and then just make up your own formula. It doesn't matter. All right, so let's shift gears now, okay? And instead of talking about sequences, I think I'm ready to talk about series. All right, series is different. So what is a series? I mean, a series is just the sum of a sequence. Aye. It's just the sum of a sequence. That's all it is. So what we're going to do is we're going to start adding up that list of numbers. We're going to start adding them together and come up with a sum. So your first example, let's say that we take this sequence, a sub n equals n. All right, that is a sequence, not a series. We know this sequence from last class is the sequence 1, 2, 3, 4. It goes forever. That's the most generic, boring sequence there is. Right? You just plug in 1, it spits out 1. Plug in 2, well, it's not boring. It's kind of like the identity sequence. All right. So now what I'd like to do is I'd like for you to add those up. So I'd like for you to take 1 plus 2 plus 3 plus 4 plus forever. Okay. So what do you think is going to happen if I do that? I'll tell you, keep adding these forever. You get like an infinity, right? It's going to be like an infinite sum, right? And that's what you start to study in calculus too. Start studying like, does this always add up to be infinity? Or is it sometimes not? And I'm going to try and tap into that just a little bit today, but right now I'm just trying to get you to understand the difference between a sequence, right? This is a sequence, and this is the series. It's just the sum of the sequence. That's all it is, right? So this is your series. And this is your sequence right there. So what we'd like to do is find some nice condensed way to write this down, because we don't necessarily want to have to write it out, each piece. So we now go after some notation. We write a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus dot, dot, dot. Let's say we go out to a sub k. So let's say we want to add up the first k numbers of a sequence. Then we will write this instead. The capital Greek letter S, that's sigma. We will put on the bottom n equals 1. And on the top, I will put k. And then here I put a sub n. This is shorthand notation for this. How many of y'all have seen that before? Summations. Yes? Yes? Carissa? Josiah? No? Okay, so the capital Greek letter S, sigma, right? S stands for sum. So this is basically telling you, hey, you're going to take the sum of a bunch of things. Here's the thing you're going to add together. It's a sub n. We're going to start with n being 1, and we're going to stop when n gets to k. So this is called your starting index. And then this is your end. And you'll always go up by 1 each time when you do a summation. That's the general formula or general notation for it. So let's see if this makes any sense. Let's say I wanted you to do this. As an example, let's write this out. Write out the terms. So if I wrote sum n equals 1 to 5 of n plus 1 over n plus 5. The part in here is your formula, okay? That's what used to be the a sub n, the formula that generates the sequence. And I want you to take it and start at n being 1, plug it in, and then add to that. Now let n be 2, and then add to that. Now let n be 3, and you stop when you get to 5. So let's write it out. So when we plug in 1 for n, what do we get? 2 over 6. I'm not going to reduce the fractions right now, just so we can see what's actually happening. Then plus, right? Now you let n be 2. 3 over 7. N is 3 now. 4 over 8. And n is 6 over. Wait, is that right? Yeah? 5? Where are we at? This was n is 1, 2, 3. Now we're at 4. N is 4. You get 5 over 9. 6 over 10. This is where we stop, right? 6 over 10. Now, could we add that up? Sure. I mean, we could get on our calculators, we get a decimal, or we could try and get a common denominator, which would be a mess. But do you all agree that this is a finite, it's a finite sum, which means that the answer to this is a number. Agreed? The answer is a number. All finite sums have an answer. All finite sums have an answer, a numerical answer. Okay. I'm trying to think about the notation here. How about we just do one more example with the notation here. Example, let's see, write out the terms of this one. Oh, no, well, sorry. 4. How about this? -3/5 to the n minus 1. So let's start plugging in our values. So if n is 1, what do you get? You get -3/5 to the 0, right? Which will be 1. Okay. And now if n is 2, this becomes a 1, doesn't it? And so then you have this to the 1 power, which is itself. So -3/5. And then if you let n be, where are we at? 2, 3. So n3 here is going to be a 2. So square this. If you square that, it's going to become positive, won't it? So you square the top, you square the bottom. You should get 9 over 25. Are we there yet? One more, right? Plug in 4. We plug in 4, we should get a power of 3 there, right? So take this and cube it, which should keep it negative, right? When you cube something that's negative, it stays negative. And then just cube the top and bottom. So 3 cubed over 5 cubed should get 27 over 125. Now, again, this is some number, right? This is some number. Why is it a number? I mean, because I know it's finite, right? This is a finite sum. A finite sum. All finite sums should sum to be some number. All right. Now, some special sums. These are ones that come up quite a bit. I'm going to put special sums, special series. All right. You know what? Let me put one more thing in here. Special finite sums. Special finite sums or series. Right, here's your first one. Sum n equals 1 to k of n. So let's write this out. What is this? If I told you to write this out, it would be what plus what plus what plus what plus what? 1 plus 2 plus 3 plus 4. And when do you stop? When you stop when you get to k, right? Okay. We actually, now we could add these up, right? We could add these up. Definitely this is going to add up to be a number. We actually have a formula for the answer. The answer to this is k times k plus 1 over 2. Do you remember me telling you about the story about the kid Gauss? That's basically the formula right there. This is the sum, if you think about it in math terms, this is the sum of the first k integers. That's what that formula gives you. The sum of the first k integers. So if you ever wanted to know, like, what is, 1 plus 2 plus 3 out to 100, there you go. Just plug in 100 for k. That's one special one. Here's another special one. Sum n equals 1 to k of n squared. So that would be, what's this written out? 1 plus 2 squared is 4, plus 3 squared is 9, plus 4 squared, 16, and then 25, plus ... until you get to the last one, k squared. Now, this formula, anyone know it? I think I know it. Hold on. I might have to reference it. I'm going to just go for out of my brain here. K times k plus 1 times 2k plus 1 over 6. I have to look it up. I just want to make sure I got it right. This would be sum of, for sum of squares. Yeah, I'm going to trust this little cartoon picture here. Yeah, I was going off memory there and I couldn't, I felt good about it, but I was just wanted to double check. Okay, so there it is. Well, it's a weird formula, huh? There it is, though. Now, I want to show you, before I get to the next formula, the first one I showed you the Gauss, how the kid came up with it and stuff, and it was pretty cool. I want to show you on this one somewhere where this could be actually used. Okay, think about if you wanted to like figure out how many blocks were in a pyramid, like in a pyramid, three-dimensional pyramid. Okay, think about how you would do that. Let's say you have a pyramid, a pyramid that has a square base to it, like this, something like that. And let's say that the bottom row of blocks, let's say, you had all these blocks in here, and there were k blocks this way and k blocks this way, right? Then how many blocks are on the bottom? On the bottom level? K squared. So we have k squared blocks on the bottom, right? Plus, now go up to the next level. Let's say there's one less block on the next level. So you got all these blocks here, right? All these blocks this way. And of course, they come across, and I didn't show that, but you got all these blocks in here, right? And so let's say that there's k minus 1 on that next level, right? Then that would be k minus 1 squared. And you keep doing this until you get down to what? Eventually you get down to like, 3 squared, 2 squared, 1 squared. So like 3 squared plus 2 squared plus 1 squared. And isn't this exactly what the thing we just did here, just backwards? It's just reversed, right? So if you just know how many blocks are on the bottom, then you can tell me how many blocks are in the whole pyramid by just plugging that into here. So let's just do it for fun. What if there were 100 blocks across the bottom? How many blocks are in this pyramid? So you have to do, I'm gonna need someone on their calculator to do this. You have to do, if this were 100 down here, 100 by 100, you have to do 100 times 101 times 200 plus 1 all over 6. $338,350. There. That was easy, right? That's a lot better than having to count all the blocks, right? Very, very efficient to do it that way. Now, I'm not proving this formula to you because the Gauss one's easier to show. This one's a little harder. You could do it, but it's a little bit harder. And then when I get to the next formula, it'll be really hard for me to show it to you. So I'm just going to wave my hands on it, and you're going to take this on faith, all right, that this formula is true. And now we're going to look at our last special sum, and that is this one, sum n equals 1 to k of n cubed. So this will be, plug in 1, you get 1. You plug in 2, you get 8. Plug in 3, you get 27. 4, you get 64. 5, you get 125. And then this stuff's growing really fast, right? And you get down to the very end, and it's k cubed. That's the sum of the cubes. The previous one was the sum of the squares. The one before that was the sum of the integers, right? So it's the integers added up, the squares of the integers added up, the cubes of the integers added up. Now check this formula out. N times n plus 1 over 2. That look familiar? Isn't that the first formula? Squared. That's weird. It's weird that it's that, but that's what it is. Oh, wait, sorry, those are Ks. Those are Ks. Those are Ks. I apologize. K plus 1 squared. Okay. Now, you understand how this formula works? Like if you wanted to know what, the sum of the cubes of the first 10 numbers, you would just plug a 10 in there, you'd be done. All right. I'm debating right now whether or not I want to go down this road with you. It's definitely a college algebra topic. I've seen it in other college algebra books. I think y'all are okay to get this. Let me see if I can make you think here a little bit. So I want to go back to this formula here. The one that Gauss came up with, okay? All right. That's the formula Gauss came up with. But I told you, when I told you the story, I told you that the formula was already known. He didn't actually come up with the formula. He just used it, and then the teacher got mad, like, where'd you get that from? So I have a question. How do you prove that this is true? Because our little geometric little idea is good, but it's not a formal mathematical proof. So how do you prove something like this? Now, I don't expect anybody to know how to prove this. That's why I'm talking about it. We actually have a formal way of doing a proof like this in math, and it's called PMI. PMI, which stands for the principle of mathematical induction. Now I'm sharing this with you because it really brings into light a very fundamental idea, all right, of how mathematicians prove things. So let me ask you, is the sun going to come up tomorrow? Why? It has every other day, right? For how long? Millions, billions of years. So for billions of years on this planet, the sun has risen, right? Just because something does something a billion times, does that guarantee that the next day or next whatever, it's going to do the same thing? Is that ever enough in mathematical language to be sure of something? Just because it does it a billion times. I can give you an example of something that does something more than a billion times, infinitely many times. And then there's one case where it doesn't do it. Watch, it's so simple to do. I'm going to define a function. And it's going to be 1 if x is not 0. And it's going to be 0 if x is 0. Okay, so think about what the graph of this function looks like. If you were to graph it, it would be 1 everywhere, wouldn't it? So it would be up 1. Let's say this is 1 up here. There, that direction, this direction, it would be 1, except here at 0, right? At 0, it would be down here at 0. So if you were to go check, if you were looking everywhere and go, oh, what's the value of this function? Oh, here it's 1, here it's 1, here it's 1. You look in both directions forever, it's 1 the whole time. Millions of times, billions of times, infinitely many times, it's 1. That does not mean it's always 1. There's one place it's not, right? So in math, it's never enough for us to try and prove something by saying, oh, look, let's check the formula. Let's plug in, you know, like if we wanted to check that, if we said, okay, what's 1 plus 2 plus 3? Okay, well, in this case, 3 is the answer, 3 is the k, right? Plug that into the formula, 3 times 3 plus 1 over 2, and you will get 6. So it checks. Does that make sense? Like we know 1 plus 2 plus 3 is 6, and it follows the formula. We can check that formula millions and billions of times, and it will always work, but that is not a proof. Okay, do you understand? That's not a proof. So how do we prove it? It's this principle of mathematical induction. And it's a very simple idea if you can put your head around it, okay? You ready for it? I want you all to think of dominoes. You all know what dominoes are? Not the pizza. You know what a domino looks like, right? This is a purely theoretical idea. Let's say I had some dominoes lined up. And these are again theoretical dominoes. So they behave in a perfect world, all right? Everything is perfect in the sense that if I knock a domino over, right, everything should happen normally. We know that in the real world, sometimes you knock one over and then it falls to the side and the one in front of it doesn't. Okay, let's just act like these behave like normal dominoes. Let's say I have an infinite line of dominoes here, okay? All these dominoes lined up. I'm going to try and see if I can come up with a logical way to convince you that all of these dominoes must fall, all right? So here's what I need to do. First of all, I need to do this. I'm going to try and show you domino which one? Domino K falls. Okay. So I'm going to go somewhere out in this list of dominoes and I'm going to pick domino K and I'm going to prove to you that it falls. Okay. All I've proven then in that case is I've proven that one domino fell, right? That's the first thing I'm going to try and do, prove to you that domino K falls. The next thing that I need to try and do is show that if domino K falls, then domino k plus 1 falls. I claim that if I can show those two things, then I have proven all the dominoes will fall. Why? Why is that enough for me? This is the big part of PMI, principle of mathematical induction, that you have to understand. Why is it that just those two things will prove that all the dominoes fall? So what do you think? If I can show you this first part, I show you, let's say that this one falls, right? That one falling doesn't guarantee me anything else, right? It's just that one falls, right? It's falling. Okay, great. But then I come and show you this. That if the K falls, right, then the one after it has to fall. If I can show you that, then how is that proving that they all fall? That's right. So if this one falls, then the one after it has to go also, right? Now, if that one goes, I use this again to say, oh, then the next one has to fall. And then I do it again for the next one. It's a very simple idea. Now, a lot of times in principle of mathematical induction, this is all you need to show, but a lot of times we show that domino k equals 1 falls. That's normally the way we use induction. We show the first one falls, and then we show that if the kth one falls, the next one must fall. And then they all fall. But you can do it for k. You don't have to do it for k equals 1. All right. So again, if we have a mathematical statement and we want to show it's true, we're going to first try and show it's true for k equals, we'll do k equals 1. Then we just have to show that if domino k is fallen, that domino k plus 1 must also fall. All right, I'm going to try to see if you can wrap your heads around this. Like I said, I've seen this in college algebra books, so this is not like out of the realm. I'm going to go to this right here. I'm going to try and prove to you this is true. Copy. So I'm now about to prove this. Right now, you are not allowed to tell me that this is true. Right now, this is a question as to whether or not it's true. All right. So first step of principle of mathematical induction. First step is I have to show that one of the dominoes falls. Let's look at the first domino. Well, the first domino would mean that let me show that this is true for k equals 1. Okay, so let's try, does this formula work for k equals 1? So if n equals 1 to 1, then I'm going to add that up, and all I get here is what? This just means add 1. Okay, now the question is, does that equal 1 plugged into this formula? Does it? 1 plus 1 over 2. That's 2 over 2, which is 1. That's true, right? That means the first domino falls. That is true, okay? With me? Now, the second thing I need to show is that if the kth one's fallen, the next one has to fall. What that means here is this. Assume it's true for k, and then show it's true for k plus 1. So I'm going to assume that the kth domino falls, then I'm going to show you that the next domino must fall, which means I have to assume that this is true for k, and then show that somehow that it would be true for k plus 1. This is the hardest part of this, okay? So first things first, let's assume it's true for k. So I'm assuming that this is true only for k, though. So that formula is true, but only for k. Now I have to show that it will give you the correct answer for k plus 1. So what is k? What is the sum? What is the sum n equals 1 to k plus 1 look like? Well, just do this. Do this, sorry, of n. I'm going to go out 1 plus 2 plus 3. How far do I go? To k plus 1, right? All the way. Now watch, I'm going to write this k, and then k plus 1 is out here, right? I want to show that that's equal to what? What do I want to show this is equal to? This formula with k plus 1 in it. So k plus 1 times k plus 1 all over 2. See, the question is this true or not? Is this equal to this? Y'all still with me? I don't know if this is true. I have to show you this is true. I need to prove this to you. I've shown the first domino is true. It falls. I'm assuming this blue one is true. And then I'm trying to show you that this is true. But watch, look. What is this? What is that? Well, we just assumed what it was, didn't we? We said that this is what? That, right? That's the kth domino. So the blue here is the kth domino. So I can replace this with k times k plus 1 over 2. And I still have next to it what? K plus 1. And the question is that equal to this? Well, let's do some algebra here. Let's distribute the k through k squared plus k over 2. Plus, let's get a common denominator, 2k over 2 plus 2 over 2. So all I'm doing here is rewriting this here, putting them all over 2's. And let's put all this together. What is that? K squared plus 3k plus 2 all over 2. Does that numerator factor? Yeah. What does it factor to be? K plus 1 times k plus 2 all over 2. But isn't that this? There, I'm done. I showed that the first domino fell. And then I said, if I assume that the kth one is falling, that the next one has to go. And so once you've shown that, then once you know the first one falls, using the second argument shows, well, then the second one has to fall. Then using the second argument again, the second one's falling now. Now the third one has to go. Okay, that's the way we prove things in math. Okay, back to series. Sorry, I've gone off. I have an ultimate goal today, and I'm still going to reach it. Okay, I gave you some special sums, and I actually showed you how to use the principle of mathematical induction to prove them. What I'm most interested in to finish off today is not finite sums. Finite sums are boring because you can always add up a finite amount of anything and get an answer. My question now is, what about infinite sums? Is it possible to add things up forever and it ever not be infinity? Let's even throw away, no negatives allowed, okay? No negatives allowed. My question to you is this: if I ask you to take some number, I'm going to say some positive number, add it to some other positive number, add it to some positive number, and keep doing this forever and ever, is it ever not going to be infinity? What do you think? Will it always be infinite? Yeah, you can have decimals in there. I don't mind if you have decimals. What do y'all think? I have another way of presenting the problem that I think will help. Let's do this. Let's say that I have a container that holds exactly 1 cup. 1 cup, right? And again, this is theoretical. This is a perfect container. We're not going to talk about evaporation. We're not talking about like molecular things and electrons. It's purely theoretical. Volume is 1 cup right there. It's empty. And here's what I'd like for you to do. I'd like for you to get a little container, and I'd like for you to pour into this 1/10 of a cup. Pour it in there, okay? So now you've got some liquid in here, right? On the bottom. Got it? Now, what I'd like for you to do is pour in 1/100th of a cup. So you've added some more, right? So the water level comes up a little bit. Got a little more in there. And now I want you to add in 1/1000th of a cup. Right? Water level is up a little bit. And I want you to do this forever. Never stop with this pattern. What's going to happen? That's what I want you to think about. I want everyone here to ponder this. The question is, will this cup ever overfill? You're never going to stop pouring in. Okay, but the amount you're pouring in is getting smaller. What do y'all think? Let's take a vote. Do I need to give you a little more time to think about it? No? Let's take a vote. How many of you think that it will overfill eventually? How about at home? Y'all have any opinions? I know I may have lost y'all with that principle of mathematical induction. So we have 3 thinking that it's going to overfill. And I'm assuming you think it's not. Okay. So
I think it's not.
you think it's not also? So let's hear arguments for both sides. I think that it's worth us hearing arguments. So who wants to argue for the yes, it's going to overfill? I'll let you both argue. Go ahead.
Well, there's a finite amount of space,
Finite amount of space,
infinite amount of time.
infinite amount of time.
So eventually, or really, it'll
It eventually will. Okay. You want to add to that? Okay. So I think the argument here that I like, which is your argument, is that like no matter what you try and tell me, this is something, right? Like this is a positive number. It's something. And if it's a finite space, if you think it doesn't overfill, then what you're telling me is that I can fit an infinite amount of somethings into a finite space. And each one of those little somethings takes up something, right, in there. So if I could do it forever, like there's no way you can contain it. Eventually, it's going to blow up. Okay, I like that argument. Makes perfect sense, logical. Hugo, you want to defend your end?
Well, we're talking about theory.
Yeah, theoretically.
Let's talk about decimals.
Uh-huh.
You can have 0.9999999 to the infinite, but still not 1. And that's how I think about it. Like it's never gonna actually fill up. It's always gonna be a little bit of space that's gonna be there.
So you think it's going to reach almost a cup, but not quite a cup?
Yeah.
Okay. But not actually ever get there because like the decimal 0.99999 is like as close as you could ever get to 1 without actually being 1?
Yeah.
Okay. I think I can follow that. Juan, do you want to add something? Because you, I think, said it's not going to fill up either.
No, yeah, I agree to whoever said
Agree?
that because you're always adding fractions, which is not really a whole.
Okay.
Even if it's gonna be a small space left, but you're always adding like a fraction of that. You're never adding the whole to fill it up.
So you think it'll get close to filling, it just won't quite actually ever get there.
Yeah, you're just adding a small bit, so it just won't
Okay.
fill up.
All right, so you ready for the answer? First of all, we will not fill this cup up, all right? We won't, which is counterintuitive, right? That goes against everything in your mind that thinks that it should. But further, we're not even going to fill it up halfway. We're not going to fill it up halfway, all right? We're not even going to get close to filling this up, right? Watch. I can convince you. It's so easy to convince you of this. Convert that to a decimal. What's 1/10 as a decimal? 0.1. What's 1/100th as a decimal? 0.01. 0.001, 0.0001. Start adding them together. What do the first two give you? First two. 0.11, and then the next one, 0.111, and then next one, 0.1111, and then it keeps going, right? Isn't this actually just equal to 0.111 forever? Yes? But that is exactly 1/9. Check it. Take 1 and divide it by 9. And if you do this, you'll remember how this works. 9 doesn't go into 1, so you have to put a decimal point and a 0, decimal point up here. 9 goes into 10 once, but then you put 9 here and you subtract, you get a 1. And so you have to drop a 0 down again. And it goes in there one time again. And then you keep doing this, you keep getting 9s under here and 1s, and you keep doing that forever, right? So that should be like a what? Okay, right? Like, how is it? This doesn't make sense, but it does. It's the fact that even though we're adding up an infinite number of positive numbers, it is possible for that to be bounded in a sense, like it not become infinite. Now, it doesn't always work this way, okay? This is a specific example. This is a very special example, actually. Some other series that we add up forever will go and blow up and become infinite, like 1 plus 2 plus 3 plus 4 plus 5. We need that these get smaller as you add them up. But how small, how fast, it depends. How about this one? What if I told you again, take a cup, and this time put in half a cup, then a third of a cup, then a fourth of a cup, then a fifth of a cup, then a sixth of a cup, right? These get smaller and smaller and smaller, don't they? This will overfill. This will overfill any cup. I don't care how big your cup ever is. This will overfill it. Why though? It's behaving the same way as the last one, right? In this previous example, each one of these was positive and getting smaller. Yes? This was positive and getting smaller also, right? It's the rate at which they're getting smaller. This is not getting small fast enough. And so it won't. So this is what you study a lot in Cal 2. You start to study this more, like, when do these go to something, when do they not? It's called convergence and divergence. And there's a lot of things you have to do to build up to it. But there's one particular type of series, one that we can talk about today. And this will be kind of like the last thing for today. I want to talk about one very special series, a special infinite series. I gave you formulas a little while ago for 3 special finite series. This is a special infinite series, and it's called the geometric series. And here's what a geometric series looks like. All geometric series look like this. It's some number a plus a times some number r plus a times some number r squared plus a times some number r cubed plus a times some number r to the 4th plus forever and ever. That's what a geometric series looks like. I will give you an example, a couple of them, so you can see it. As an example, very simple one, 1 plus a half plus a 4th plus an 1/8 plus a 16th plus a 32nd plus ... Can you all see that that's a geometric series? Can you identify the A and the R? Can you tell me what the A is? Can you tell me what the R is here? A is 1, R is a half. Right? Because this is like, here's A is 1, and then this is If all these A's are ones, then we just really need to look at the R. So this should just be R, R squared, R cubed, R to the fourth, R to the fifth. So yeah, that looks like 1/2 squared. So could I rewrite this then? Could I rewrite this as sum n equals 1, watch this, to infinity. You see how I put an infinity up here? That means I never stop. What would this be? How could I make this happen? Think about this 1/1 here. What are all the numerators? 1. Okay, so I can leave all these as ones. And then how do you create the denominators? 2, 4, 8, 16. Those are all powers of 2. Starting with this one, though, what's this right here? 2 raised to the 0. So you need to start at 0. Our index starts at 1. So 2 to the what? N minus 1. Good. That would be the series formula for that geometric series. Now, with that in mind, is there a way you could come up here and rewrite this? Let me move this down. Is there a way you could maybe rewrite this here? Let's go n equals 1 to infinity. Okay, what do all of these have in common? They all have an A, right? They all have an A. And then the powers on the R's are going to be 1, 2, 3, 4, but it starts here with a hidden R to the 0. So we're going to put here R to the what? N minus 1. That make sense? That is what a geometric series looks like. Let me give you another example, and you tell me whether or not you can identify what A and R are. What A and R are? Okay, how about this one? How about three fifths minus 9/25 plus 27 over 125 minus, where are we at? 81 over, what is that? 625? Come on, man. All right, 625 plus dot, dot, dot. Now, I think it might be hard initially to figure out what's going on here. So let's just break it down the way we were breaking these things down in the very beginning of class. What's the formula creating those numbers? They're exponential. They're alternating, right? They're alternating. So I would use like -1 to what power here? I want to start positive, right? Positive then negative, then positive then negative. So we need n will start at 1, right? What I'm trying to do is come up with an A sub n, a formula for this. So like an A sub n to create the numbers. -1 to the, I want it to start positive. N minus 1 or plus 1, your choice. I'm going to put n minus 1. What about the numerators? 3, 9, 27, 81, 3 to the n over 5 to the n. You all with me? This should do it. -1 to the n minus 1, 3 to the n, 5 to the n. That should create this, right? So for us, we are now going to convert it into the series. So we got to turn it into sum n equals 1 to infinity of -1 to the n minus 1, 3 to the n over 5 to the n. Now, I don't know yet what A and R are, okay? I just want you to see how we converted it over, all right? Questions on this? Now for the trickiest part. How do we make it look like this? How do we make that look like this? Do they look the same right now? Do I have some number by itself in front of something raised to the n minus 1? Not really. I do have an n minus 1 on this right here, right? But do y'all see that this and this don't have n minus 1s on them? Y'all see that? All right, I'm about to get extremely clever. You ready? Watch. I'm going to do something mathematicians like to do whenever they get stuck on something where they need something to be there that's not there. I'm going to go 3. I really want it to be what? N minus 1? So I'm going to go n, and then here's what I'm going to do. That's what's there, right? 3 to the n. I'm going to go minus 1 plus 1. All right. And then on the bottom, I really want that 5 to the n to be a 5 to the n minus 1. So I'm going to go minus 1 plus 1. Now, why? Let's see why I did that and what I can do with it. Sum n equals 1 to infinity. All right. Just take a look at this piece right here. If I can just make sure you, if I can make sure you understand this, the bottom part will be easy. Do y'all agree that that's the same as 3 to the n minus 1 times 3 to the 1? Remember properties of exponents? That if you have the same base and you have different exponents, you will add these two exponents together if that's multiplication, right? So I'm basically taking this and I'm peeling it backwards, right? I'm going to take it from here back to here. And then I'll have a 3 to the n minus 1, and then there will be a 3 next to it. See, isn't that clever? So I'm going to go negative 1 to the n minus 1 times now a 3 to the n minus 1, but I have a 3 next to it. What about the bottom? 5 to the n minus 1 times 5, right? Now look at all the stuff that has the n minus 1 power on it, right? All those have an n minus 1 power. Let's put them all together, which means to the negative 1 times 3 and then divide by 5 and raise that all to the n minus 1. So this becomes, let's see, these two out here, those don't have n minus 1 on them, right? So I'm just going to move that out to the front. 3/5. And then here, all of that together gives me negative 3/5 to the n minus 1. And now do you see the A? You see the A? The A is this, right? The A in the formula. See if I can move this. Yeah, the A here is this. And then the R here is this number. See it? So I had to take the expression, right? Let's just kind of back up. I took this, right? I took this. I rewrote it using a formula, just kind of thinking, right? Thinking through it like what we did in the previous section. It was like, oh, can I come up with a formula with it? Then I threw it inside the sigma notation. And then what I did is I said, oh, crap, I need it to look like this. So I need n minus 1s. So I made it happen. I massaged it and got it to what I wanted it to look like. And then it all worked out. All right. I'm going to give you some problems like that to practice on your own. All right. For homework. What's the whole point of this? We actually know what this does. Like I said, some things add up like this, that adds up and it blows up. It gets infinitely big. But this one, these got small enough fast, right? Look at this right here. This is a geometric series. All right, it is. I won't go into it now. What I'd like to kind of end class with is I want to show you what this does. Okay, I want to show you what this actually turns into. So for a long time, mathematicians wondered, okay, for a long time, mathematicians wondered, is this sum, okay, is this infinite or finite? Right? That was the question. Is that going to just get bigger and blow up? Or is it like the 0.1111111 where it's, 1/9 and it doesn't blow up? So someone finally figured out a clever way of coming up with a way of finding out what it does. And here's what they did. It's actually pretty elegant and nice once you see it. So the idea here is this. They said, let's look at what happens if you take just the first well, you know what? I think I can do it this way. Let me see. Yeah, let me do it this way. So I'm going to do, they said, let's just take the first K of these. Okay, so they said, let's just look out and let's stop at K. So we stop somewhere, okay? Let's call this S. And I'd like to know what that sum is. So then this is the part that's completely weird. Like, again, you wouldn't think of doing this. They took that and they multiplied that S by R. Now, when I do that, let's see what happens. What does A turn into? AR. And the next one? AR squared. So I'm just basically taking this expression and multiplying everything by R, which increases the powers. So AR cubed. AR to the 4th. Yes? And this keeps going. Now, careful. At the very end, what am I going to have at the very end? AR K plus 1. I have to add 1 to that exponent, right? Because I added another R in here. So I have one more. Good? Why? Why do that for this step? Take that top row and subtract the bottom row. So I want you to take everything here and subtract this. And look at the way I'm going to do it. I'm going to take this S and subtract RS. So my left side becomes S minus RS. I'm just taking that, subtracting this. That must equal, now, this A doesn't have anything to subtract with, right? So that A is still there. But what about everything else here? Gone, 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 gone. Okay, what about this last one? Is it gone? This one right here? Yes. It cancels with actually the one right in front of this one, isn't it? It's right there. This is AR to the K is right before this one. So those cancel. But what's still here? This one, right? This one. And I'm subtracting it. So I still have down here minus AR to the K plus 1. With me? We're getting close. This is going to be really cool. On the left side of this equation, factor an S out. Okay. Now divide both sides by 1 minus R. So look, earlier I said S is what happens if you add up the first K terms, right? S is what you get when you add up the first K terms. What I'd like to know now is what would happen if I let K get huge, right? Because think about this. The bigger K gets, the further out this sum goes, right? And I want to go forever. But look at this nice, tight, compacted expression for S now. What would happen if I let this K right here, that K, become a huge number? Think about how it would impact R. Well, won't it depend on R though? Think about it this way. If I tell you that the absolute value of R is less than 1, think about a number that's like a decimal, like maybe like 0.7. What would happen if you take a number like 0.7 and start raising it to huge powers? Does it get bigger or smaller? Smaller, right? It gets smaller. If you take a decimal like 0.7 and start raising it to big powers, 0.7 squared, 0.7 cubed, it gets tiny. Now, if the absolute value of R is bigger than 1 or equal to 1, then it's going to blow up, because then you're taking that number and making it huge. So imagine this case. If the absolute value of R is less than 1, then everything here, as K gets big, what does that go to? It goes to 0, it gets squashed down to nothing. This heads to 0, which kills everything off here, which leaves you with what? A over 1 minus R. And that's the formula for it. So as long as the absolute value of R is less than 1, the sum of the geometric series will be A over 1 minus R. That's an important formula to know. So I'm going to give you a final example here. Let's look at the problem that we did when we were pouring the water in. Okay, I showed you already that that's 1/9 by doing 0.11111, right? But I'm going to try and show it to you a different way. If we take 1/10 plus 100th plus 1,000 forever, I can look at that as being the sum n equals 1 to infinity of 1 over 10 to the n. Do we agree? You plug in 1, then this is 10 squared, 10 cubed. So that's the formula for it. I would love to make this look like a geometric series, AR to the n minus 1. That's what all geometric series look like. So can we get it to look like this? Well, first thing is I can rewrite that as 1/10 to the n. Does that change anything? No, because I can apply the nth power to the 1 and to the 10. It's going to give you the same answer, right? Because 1 to any power. So got that. That's looking closer. I need this to be an n minus 1. How do I make that happen? -1 and +1, right? So I'm going to do that on the next line. This is equal to sum n equals 1 to infinity, 1/10 to the n, here it comes, -1 plus 1. But that equals sum n equals 1 to infinity. Now I've got a 1/10 to the n minus 1, right? And a what? And a 1/10 next to it. So I'm going to write it this way, 1/10 to the n minus 1. And now does that look like geometric? Yeah. What's that? They're not always that way. No. For these examples so far, they have been the same number, but it won't always be that way. So this is A, right? And this is R. Now, is the absolute value of R, if R is 1/10, is the absolute value of that less than 1? It is, right? So since the absolute value is less, since, I'm going to keep this, yeah, I'm out of space on this page. So since R is 1/10 and the absolute value of that is less than 1, what can we say about this series? What should it add up to be? The sum should be A, right, which is 1/10 over 1 minus a 10th, which is 1/10 over 9/10, right? Subtract 1 minus a tenth is 9/10. And 1/10 over 9/10, if you just do the reciprocal, you get what? 1/9, which is exactly what I said it was going to be, right? 0.1111 forever. All right, so here's what I'd like for you to do, just as a homework. I think this will encompass a lot of what we've done here today. I'd like for you, I'm gonna write it down a few series, and I want you to basically figure out what their formulas are, and then all of these are going to be geometric, okay? And I want you to convert them into the geometric series, find A and R, and then look at R, make sure the absolute value is less than 1. If it is, then tell me what it adds up to be. All right, so first one here, we'll keep this first one is going to be real basic. It'll be 1 plus 1/4 plus 1/16 plus, I think that's enough to get the pattern there. So again, I want you to find the sigma notation of this. Okay, that'll be the first thing. And then write it as a geometric series. Find A and then R. So these, for all of these, that's what you're doing. Rewrite it. Find A and R. And then the last step would be to find S if the absolute value of R is less than 1. If the absolute R is bigger than 1 or equal to 1, then this thing sums to infinity. It gets huge. So you would just say doesn't sum to a number. All right, this next one, we'll do 2/3 minus 4/9 plus 8/27 minus 16 over 81 plus ... Next one. Hold on. Let me do it this way. 8/10 plus 16 over 100 plus 32 over 1,000 plus 64 over 10,000. I'm not reducing those on purpose so that you can figure out the pattern. And then the last one is going to be the hard one. This fourth one is more of like a bonus. All right. I want you to take this decimal 0.252525. All right. So the 25 keeps repeating, 252525. I want you to see, can you write this as a sum? Write as a sum. And then try and do everything here. I'm going to give you a hint on this one, okay? Just a hint. I'll put this back up in a minute. When we were doing this problem right here, 0.111, first thing I did, well, I worked backwards here. I gave you the fractions, right? And then from the fractions, you turn it into decimals, and from the decimals, you turn it into the repeating decimal. I have now given you the repeating decimal. I want you to go back to here, and then once you get it to this, can you turn it into the geometric series? It's a little harder, especially because I haven't given you an example, but it's a good exercise to see how you do with it. All right, I think we're out of time. So today, I know today has been kind of like all over the place. We had sequences and principle of mathematical induction. How much of this do you need to know? On Wednesday, I will cover, I will talk about the final. I'll talk about here are the topics, give you all some sort of review for it. And then that'll be it. We'll be done. Any questions?
When will the final be?
It's a week from Wednesday. So on our, believe it's on our schedule here. It's on December 8th, 12:30. So you have to pay attention to that. It's 30 minutes earlier than we normally meet. And that's a college thing. It has nothing to do with me. So, but it will be face-to-face on campus. It won't be over Zoom. And
Okay.
it goes till 3:15.
And all of this is on the test.
Well, that's why I think Wednesday you should be here. Yeah, this will be on here. I'm going to give you some sort of geometric sequence. So look, in our schedule here, it talks about arithmetic sequences and geometric sequences. I've gone beyond this. So an arithmetic sequence is basically any sequence that jumps by the same amount. You know how when we started, you're asking like, hey, if it jumps by 3, it's just 3n. If it's 2, it's 2n. If it's 5, it's 5n. That's an arithmetic sequence. Okay. Geometric sequences, here they're just getting you used to the notation. I've gone all the way into series, which is beyond this, just because I think y'all can handle it, see how it goes. So be here Wednesday so I can give you some idea of the questions that I will ask on the final, which I think are going to be very similar to what I just sent you home with. Because you have to kind of be able to come up with the formula and then use things. Yes. That's it? Okay. Juan, does that answer your question?
Yes, sir. I'll be there on Wednesday.
Okay. Yeah, either be here or on Zoom. Either way, I'm going to Zoom on Wednesday, but just saying be present for. Okay, have a good one. It's finals week, which means that you should only meet once. Yeah, it's supposed to be where everyone's studying, right? So you're supposed to meet for your lecture and that's it. I mean, for your final and that's it. No